Okay, today we're going to talk about power factor correction, which should take somewhere between 20 and 30 minutes. And then after that, if you guys have any questions regarding any of the homeworks or any of the steady state sinusoidal concepts, I'd be happy to answer them. On Monday, we are going to take our knowledge of steady state sinusoidal circuit analysis and apply it to the concept of filters. So let's get started with power factor correction. So as we discussed a bit on Wednesday, power factor is a measure of the efficiency of an electrical system. Specifically, it is a measure of how efficiently a source, like a transformer or a substation or something like that, delivers power capable of doing work to a load, like an electric motor or a portion of a factory or something like that. We as consumers pay for the average power that we consume, but industrial suppliers like power plants have to pay for the apparent power that they generate. And so if the power factor at which your load is operating is too low, meaning that you are using the power that's generated too inefficiently, you will be fined. So engineers have come up with solutions to avoid paying these fines by using a process called power factor correction. So let's look very briefly at the power triangle for a generic inductive load. And we're only going to consider power factor correction for inductive loads because capacitive loads don't really occur pretty much ever in industry. So if I'm looking at my real axis here and my imaginary axis here, a generic inductive load might be something like this, where I'm going to project this onto the real axis. And I'm going to call this guy P old. And I'm going to project it onto the imaginary axis. And I'm going to call this guy Q old. And I guess while I'm at it, I should call S old as well. And similarly, we're going to have some angle theta S old. So this is our system before power factor correction is applied. Now, the goal of power factor correction is to increase the power factor from some number, whatever it happens to be. So typically speaking, some number lagging that's less than, let's say 95%, up to 95% lagging or better. So if we wanted to cause the power factor to increase, would we need to increase the angle or decrease the angle theta S? We need to decrease the angle theta S, okay? There's two ways that we can go about doing that. I will just describe one way that's wildly dumb and explain why it's not done. The first way, and this is the dumb way, would be that we would increase the average power absorbed by our load while holding the reactive power constant. So effectively, we would put resistance in series with our load. What that would do would cause the angle to go down because the real portion is getting larger while the imaginary portion stays the same. So that angle is going to be smaller. However, we are avoiding a fine by paying a higher utility bill, which makes no sense whatsoever, right? So that is mathematically a way in which you could correct your power factor, but it is not ever done in practice because it's more expensive than paying the fine usually. So instead, we need to develop a means by which that we can lower the reactive power. So let's say that I decrease my angle to this point. So I'm going to call this guy S new. It has the exact same average power as before, but if I project my reactive power onto the imaginary axis, where this guy is Q new, I can see easily that decreasing the reactive power absorbed by my load will lower my power factor angle. So I'm going to call this new angle, and I'll do it in this color, theta S new. So the question then becomes, well, how can I decrease the reactive power absorbed by my load? And the short answer is I simply put a capacitor in parallel with it. The complex power relationship specifically for a capacitor. So let's look at SC, or let's call it S cap. By definition will be the voltage drop, RMS phasor voltage drop across the capacitor multiplied by the current conjugate flowing through the capacitor. So I'm going to use, let's see, I'm going to use Ohm's law to express the current flowing through my capacitor as a function of the voltage drop over my capacitor. And so that would give me V cap times, let's see, I'm just going to do V over Z here. So that would be divided by 1 over J omega C, or actually a better way to put this might be negative J over omega C. I conjugate this whole guy, right? Conjugating that fraction. Well, what that's going to give me is I'm going to have, so I have something divided by negative J divided by omega C, which is going to give me an omega C in the numerator. So let's start there. I'm going to have my capacitor voltage multiplied by its complex conjugate, which is just going to give me the magnitude of the capacitor voltage squared. This is typically written as just VRMS squared. And now I have that factor of negative J in the denominator. But when I conjugate it, it's going to be positive J in the denominator. But when I divide by J, it's the same as negative J. So I know that it may not make a whole heck of a lot of sense, but think about what's going on here, right? So I change the sign on this J by doing the conjugate operation so that I'm dividing by J. And dividing by J is the same thing as multiplying by negative J. So that's why this negative sign winds up surviving. So I wanted to be clear on that. So this is the complex power that is absorbed by a capacitor, and we can see that it is always a negative quantity. So capacitors are used in these circuits to effectively supply reactance to the system so that the industrial source doesn't have to do that. So that reactive power doesn't need to be supplied by the utility company, which means they don't have to pay for it, therefore they don't have to fine you for making them produce it. All right, so now that we know why the capacitor is the missing piece of the puzzle here on how to do power factor correction, let's walk through the mathematical process with a simple example problem, okay? So let's say that we have a voltage source, and let's make it 600 angle 0 degrees volts RMS. We have a transmission line, which I am representing by an impedance ZW that I'll define momentarily. And then connecting the transmission line is connecting our source to an electric motor, which I'm representing with a circle with a letter M in it, that has a specific impedance of ZM. And let's say it's got a low resistance, so something on the order of 10 plus J 70 ohms. So low resistance, very high reactance, which would make sense for an induction motor. And for the sake of argument here, let's say that my wire has an impedance of 0.1 ohms plus J 0.05 ohms. So we should see that for any real transmission line, it's going to have some real resistance, representing the resistance of the copper over that long period of long section of wire. And it's going to have some inductance inherently, because any conductor in a closed circuit exhibits inductance. If you haven't learned that yet, you will in your physics class or your electromagnetics class. So we should see that any transmission line should be represented, if it has losses in the line, by some resistance plus some inductance. So the first thing that we are going to do is figure out what power factor this system operates at, which should be fairly straightforward, right? Then we are going to try to correct the power factor to some specified level, and I'll tell you what that specified level is once I figure out what it is. Another piece of information, just so that I don't forget it because we'll need it, is we're going to say that our source is operating at a frequency of 60 hertz. So this would be an industrial voltage here in the United States. All right, so who can tell me how I would go about determining two pieces of information here: the complex power that's being supplied by my source and the power factor at which my source is operating? Okay, so Mr. Wickland, I believe, is suggesting that we could combine our transmission line represented by ZW and our motor represented by ZM into a single impedance. And then the angle of that equivalent impedance will be identical to the power factor angle. That is absolutely correct. So let's go ahead and do that real quick. So I'm going to just call this Z, ZS, the impedance seen by my source, which is going to be ZW plus ZM, which would be 10.1 plus J 70.05 ohms. And in polar form, that will be 10.1 plus 70.774 with an angle of 81.795 degrees. So from this, the power factor at which our source operates is simply the cosine, let's see, that is X, of (81.795 degrees), which I get to be 0.143. And it's lagging because the angle is positive. So we can see that this is a very inefficient system, right? We're operating at effectively 14.3% efficiency, which means we're going to have very large fines. Now, in order to determine the size of the capacitor that we're going to have to place in parallel with our source to correct for this, we need to know what the average power of our that is being absorbed, or the average power being supplied by our source is prior to power factor correction, because we're going to hold that term constant, right? So this brings us to the second part of the question I was asking. We needed to know the power factor, and we need to know the complex power supplied by our source. Because if we know the complex power supplied by the source, then we automatically know what the average power is, the reactive power is, the apparent power is, the power factor angle, blah, blah, blah. So anytime I'm looking for any power quantity, I usually wind up computing complex power because that has all of the information kind of buried within that one figure. So how can I figure out what the complex power supplied by my source is? Okay. So you are suggesting, okay, so VRMS squared times wouldn't it be divided by the magnitude? Right? So VRMS, the magnitude of the RMS voltage squared divided by the magnitude of the impedance multiplied by the cosine of theta z, I believe should give us the average power specifically. Yeah, so that would give us the average power, which is really what we're most concerned with right here. To get the complex power, if we know what the voltage is, and we know what the total impedance is, we should be able to get the complex power pretty easily, just to make sure we're getting everything effectively. So I would argue that the complex power supplied by the source is going to be the RMS phasor voltage of the source times the RMS phasor current that's leaving the source conjugate. And we could figure that out using Ohm's law, but we actually don't really need to. And so what I mean by that is we have VS times VS over ZS conjugate is the same as the magnitude of VS over squared over the complex conjugate of ZS. So we have all the information without actually doing any other mathematical steps. So our complex power here should be 600, absolute value of 600 volts RMS quantity squared divided by 70.774 angle negative 81.795 degrees ohms. And in doing this, I'm going to get the answer and I'm going to express it in rectangular form. So 600 squared divided by the conjugate. $725.892 plus J 5,034.525 volt ampere, where that 725.892 is the average power. And just to do a sanity check here, if I did 600 squared over 70.774 times cosine of 81.795, 725.937. So with a little rounding error, it's still the exact same thing as what you suggested. So just my personal preference is always to just find the complex power again, because it has all of that stuff inside of it. You don't have to do it that way, but that's just my preference. All right, so now that I know what power factor my load is operating at, 0.143 lagging, and I know what my complex power that my load is operating at, let's choose a target. Okay, so what do we want to increase the power factor of this system to? Let's just pick something. 95%, leading or lagging? 95% lagging. All right, so our old power factor, to be clear, PF old was 14.3% lagging. Excuse me, I'm about to sneeze. Our new power factor is going to be 95% lagging. So how can we use, yes, I'm not going to sneeze. How can we use this information to determine the new complex power after power factor correction, which we'll call S new? Any thoughts? So we are going to wind up finding the reactants, but that's not a really straightforward way of looking at things. And so what I mean by that, we know the average power absorbed by or supplied by our source after power factor correction, because we know that that does not change, right? And we know, or we can infer the power factor angle that we're looking for because we know the power factor target, right? So using the definition of power factor, PF is equal to P over S, which is the same as cosine of theta S. We know what P is. We know what the power factor is. So we should easily be able to determine S and theta S just from this relationship, right? So I would argue that P, 725.892 watts, divided by our power factor of 0.95 gives us the apparent power of our system after power factor correction. And if we take our angle to be the inverse cosine of 0.95, that's going to tell us exactly what our complex power after power factor correction should be with a 95% lagging power factor. So if we do the math here real quick, so let's see, what did I save that as? All right, so on my calculator, I'm going to just take, if it'll let me, the real part of what I have stored as X, divide that by 0.95, and then given an angle of the inverse cosine of 0.95, and I get, express this in rectangular form. Oh, I got something wackadoo. Okay, I didn't have my variable saved right. That's not a problem. Let me just type it in the way that we have it. 725.892 divided by 0.95 with an angle of inverse cosine of 0.95 and rectangular number. So I get 725.892. That number has to stay the same or we've made an egregious error, plus J 238.589 volt amperes. Okay. So now that we know what S new is, the difference, S new minus S old, has to be what the capacitor supplied to the system, right? So I'm going to say that S cap is simply S new minus S old. And so that is 238.589 minus 5034.525 is negative J 4795.936 volt amperes. This number needs to be negative. Okay, if it's not negative, you've done something wrong. So our capacitor should be absorbing negative 4.79 kilovolt amperes or supplying positive 4.795 kiloamperes. So what we're going to do now to determine the value of C that makes this happen is revisit this definition right here, right? So we know that S cap is negative J omega C times volts RMS squared. So we're just going to set these guys equal to each other. Negative J omega C volts RMS quantity squared. And then we can solve and say that C is going to be, so this negative, the negative J's cancel out on both sides. So I should have the magnitude of S cap divided by omega times the volts RMS squared. So that would be 4,795.936 volt amperes divided by 120 pi, because omega is 2 pi times our linear frequency of 60 hertz that we introduced earlier, times our quantity 600 volts RMS squared. .338 microfarads. So let me ask you guys a simple theoretical style question, and then that'll, I think, will be enough for power factor correction. We've talked about the different steps involved in calculating it and all that jazz. But this is a question that I was asked a couple of years ago in circuits 2. Does it matter where we place our capacitor? And so what I mean by that is, in this problem, we assumed that we put our power factor correction capacitor right there in parallel with our voltage source. But another option might be, to put it just in parallel with the load. Both ways would wind up correcting the power factor, right? And technically, we would need a smaller capacitor if we only considered the motor, right? Because since our transmission line has some associated inductance with it as well, when we place our capacitor in parallel with our voltage source, we are correcting that the reactance of the line as well. And so my student asked, you know, why would you ever do one versus the other? And it's purely from a cost perspective, right? So for instance, if you only have a few loads that are screwing up your power factor, it may be reasonably cost effective to just correct at those specific loads. But if you're running a large scale industrial plant that has lots of HVAC units and conveyor belts and things like that that rely on induction motors, it's probably going to be cheaper in the long run to correct your power factor where your power at the source of campus, right? So it really just depends on what you're looking for. If you only need to correct it in a couple of places, it's probably cheaper to do it with the load. For a large scale operation, it's usually going to be cheaper to do it at the transformer itself. All right, any questions regarding power factor correction or anything like that? All right, nobody's saying much of anything. Does anybody have any questions about any of this sinusoidal steady state stuff? So anything we've talked about, any homework problems that you're struggling with or just need a little bit of clarification or anything on? Mr. Burrell, I think your hand is up.
First, I'm a little late, but I want a question very first. Homework set for sinusoidal.
All right, let me pull it up on WebWork real quick. Or not WebWork. Problem 4. Okay. So 223. So that would have been in the this guy. Did I put it here? Homework 11? No. Maybe it was here. There we go. All right. Problem 4, you said, right? All right. Find the value of the capacitance C such that I of t will be in phase with the source voltage, V of t, blah, 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 blah. Okay. So, yeah, this one can definitely be a little bit tricky. So let's take a look at really the approach that we're looking at here, okay? So we have some voltage source, Vs, and then some resistance, let's call it R1. We have some capacitance, some resistance, R2, and then we have an inductance here, right? Okay, so we know what our specific frequency of operation is, omega, because we're told what frequency our voltage source operates at. So really what we're looking at here is how can we make everything to the right of this dashed line look purely like a resistance. Because if it looks purely like a resistance, then our voltage V of t and our current I of t will be perfectly in phase, right? So if I'm looking in through those terminals, I see this network, right? I have 1 over j omega c in parallel with R2 plus j omega L. So my goal is to figure out what value of C makes that parallel combination behave as if it were purely real. Is that a reasonable way to approach this? That makes sense? All right, so let's see what happens when I multiply these guys together, okay? So I'm gonna have a ZEQ is equal to R2 plus j omega L times 1 over j omega C. And then down here, I'm gonna have 1 over j omega C plus R2 plus j omega L. Right? It will either be negative j over omega C or positive 1 over j omega C. Unless, yeah. Okay. Yeah, so the reason why that is if we take, so just as a quick aside here, 1 over j omega C, this comes from our fundamental relationship of what impedance is, the ratio of the phasor voltage to the phasor current for a capacitor. This is the same thing as 1 over j multiplied by 1 over omega C. Well, j to the minus 1 power, 1 over j times j over j, gives us j over j squared, which is negative j in the numerator. So we can call this guy negative j over omega C as well. So it's either this one or this one, but it should never be negative j in the numerator divided by omega C. So let's, once I finish erasing all this jibber jabber, let's go back up here a little bit. So how I might approach this from this point, and it's been a couple of years since I solved this guy, so I'm just spitballing here. The first thing I might do is multiply by a factor of j omega C over j omega C to get rid of the fractions inside my fractions. And so this would leave me with, let's see, I'm going to have j squared, which is going to give me negative 1, right? Times, oh wait, actually, no, I'm doing something stupid here. All right, so in my numerator then, that's simply going to be R2 plus j omega L. But here in my denominator, I'm going to have 1 minus omega squared LC plus j omega R2C. Did I do my algebra correct here? Anybody? Okay. So what I would do after this is I would multiply by the complex conjugate of my denominator over the complex conjugate of my denominator. And so what I mean by that is I would say 1 minus omega squared LC minus j omega R2C divided by 1 minus omega squared LC minus j omega R2C. Let me block these guys off like so and like so. What that's going to do is get rid of all of the complex numbers in my denominator, okay? They no longer matter to me, so I'm not going to bother going through what that is, although it shouldn't be too particularly difficult to do. My whole point here is if I eliminate all of my complex numbers from the denominator, all I need to do is look at the imaginary part of the numerator and set that equal to 0, and I can solve for whatever C makes that happen, right? So Let's see, what I'm going to have in my numerator then would be R2 times 1 minus omega squared LC minus j omega R2 squared C plus j omega L 1 minus omega squared LC plus omega squared R2 LC all divided by whatever the denominator happens to be, right? That makes sense? Anybody see any algebraic errors or anything like that? So if I want this guy to behave as a purely real impedance, then what I'm going to do is I'm just going to take the imaginary part and set it equal to 0. So I am saying that omega L times 1 minus omega squared LC minus omega R squared C is equal to 0. Because if that imaginary part is equal to 0, then the impedance of the overall system is purely real. Does that make sense? All right. So I see that I have a common factor of omega that I could get rid of. So I'm going to say, let's say L1 minus omega squared LC is equal to R2 squared C. Let's see. So that's going to be L minus omega squared L squared C is equal to R2 squared C. So L is equal to C multiplied by omega squared L squared plus R2 squared. And therefore, C should be L divided by omega squared L squared plus R2 squared. And that will be the value of the capacitor that makes my system behave as if it sees a purely real impedance. That's kind of fundamental to an impedance matching network or something like that, which you'll talk about probably to some extent next year. It's ways to make loads look like different things so that when you connect it to a particular source or measurement circuit, you don't get weird losses and resonances and stuff like that. Anyhow, that fairly answer your question? All right. How can I help you? Same one. All right. Anybody else have any questions about any of the homework problems or anything? Homework 12. Problem 4. All right. So homework 12 is the one on this one, I think. And you said problem 4, correct? So you're asking specifically about this. Okay, so that would entail what is called so this would be what's considered a delta network. And so in order to do a resistor combination technique here, you would have to do what's called a delta to Y conversion, which I believe I made you guys do that strictly with resistors way back on homework set number 1. Those exact same rules apply for impedances, so you could do that. Another methodology could be disconnect this guy, this impedance ZL, and then find the open circuit voltage and find the short circuit current and use that fundamental relationship for Thevenin and Norton's being equivalent circuits to find the Thevenin equivalent impedance. And since you need to know V Thevenin anyway, I would argue that's probably the easier method. So disconnect ZL, find V Thevenin, replace ZL with a short circuit, find I Norton, and then the ratio of V Thevenin divided by I Norton gives you the Z Thevenin that you're looking for. Yeah.
immediately went for looking for R7 and
Yeah, and you can absolutely do it that way, but you have to do a delta Y transformation here because of the way this guy is set up. So when you converted this to a Y network, the 2 ohm resistor would be in series with something, and then you'd have a resistance or impedance over here, and then impedance over here, and it would then the network would simplify easily. But I understand why that's not your go-to thought because you've only done it once ever. So it seems reasonable. But using the fundamental definition for Thevenin voltage, V Thevenin divided by I Norton will get you there really quickly because you've already done half the work anyway. Any other questions on any of the homework assignments or anything?
the only real question I've got is how and just off the top of my head. You end up basically with 2 DC power.
Homework 13. So let's see. All right.
Basically, what I looked at is you end up with 2 frequencies. So one question is once you calculate all your powers, basically you got 2 different powers, right?
So you should have 5 different power contributions because you have 2 different frequencies, right? So you should have a DC, you should have 2 DC terms. You should have 1 term that is at twice 25. So you should have a omega is equal to 0 term, and omega is equal to 50 term, and omega is equal to 40 term, and an omega is equal to 5 term, and an omega is equal to 45. So you're going to have 2 contributions at DC, 1 contribution at double this frequency, 1 contribution, double the 25 radians per second frequency, 1 contribution at double the 20 radians per second frequency, and then you're going to have 2 contributions consisting of when you take the difference of these guys, and 2 contributions when you add them together. So your instantaneous power should have 5 terms, 1 corresponding to DC, then 5 radians per second, 40 radians per second, 45 radians per second, and 50 radians per second. And then your your average power is just the DC portion. Really tedious, but follows exactly the example thing I did in class symbolically. It's because when you take the product of 2 cosine functions, you get a portion that is, 1/2 times the cosine of the difference of the angles plus 1/2 the cosine of the sum of the angles. So when you square these guys effectively, that's where you get your DC terms from and your double frequency terms from. And when you cross multiply them, that's where you get the difference terms and add the frequencies together terms. So it's just a lot of ugly math, unfortunately. So superposition cannot be done for the instantaneous power. Well, I'll take that back. You have to do superposition in as much as you have to use superposition to find Vx of t and Vy of t, but Vx of t is going to have 2 frequency components, and Vy of t is going to have 2 frequency components. And then you have to do all of that cross multiplication crap in the time domain. You can't do it so you're doing the superposition in the frequency domain to get how this behaves at this frequency and how it behaves at this frequency. Then you have to do all of your other work in the time domain. Yeah, and you can't do that because these guys are operating at different frequencies. So you cannot do any comparison of, Vx at one frequency to say Vy at the other frequency. It's like comparing apples and snails. It's not even a fruit, you know, it's way the hell off. So yeah, no, that's a common mistake, and that's what makes these types of calculations so tedious, and which spurred on the creation of complex power, so where you don't have to worry about all that kind of crap. Right? Because for a complex power circuit, it doesn't matter what these frequencies are. The RMS value of this guy is 5/√2. And the RMS value of this guy is 120/√2. Like, so there's I think, problem 3. Yeah, so problem 3 is you have 3 different frequencies. Okay, so let's, without going into a terrible amount of detail, because we really already did that in the multi-frequency power lecture. When you have a periodic signal that has multiple frequencies, the effective value, let's just call it a voltage, just for the sake of argument, but it would be the exact same thing for the current, is simply going to be the effective value at your first frequency, which I'm just going to call it omega naught squared, plus the effective value at your second frequency, which I'll call omega 1 squared, plus your effective value at your third frequency squared, and so on and so on. So for that particular problem, you don't even have to take the integral. That's the thing. So, and let me explain that real quick, right? What's the effective value of the constant term? Because that's a frequency, right? So the effective value of 5 is 5, right? That's the wrong thing. Where am I at? So this would be the square root of 5 squared plus, all right, let's circle back to that guy. Now we have a signal that is 12 cosine 10t plus 30 degrees. So what's the effective value of that guy? I just want the magnitude of the, it's a sinusoidal signal. What's the effective value of any sinusoidal signal? The magnitude divided by the square root of 2, right? So we would put in 12/√2 here. And now we have our omega is equal to 20 radians per second. And so that's going to give us 8/√2 squared here. Do this, that's the answer. And it is, because all those cross multiply terms and all that kind of crap, when you take the integrals, they go away. It reduces to this simple thing where it's just the effective value at one frequency squared plus the effective value at the second frequency squared plus the effective value at the third frequency squared, and so forth and so forth and so forth. So you could struggle to do that analytically, but qualitatively it has to behave that way, because you know that the integral of all those cross multiplied terms has to go to 0. When we saw that when we calculated the average power. Yeah. All right, anybody else got anything? All right, see you guys on Monday, where we're going to talk about filters.